Hello everyone, I am Alipriyo Hoory. I am a PhD student from Indian Institute of Technology Madras, Chennai, India. Firstly, I want to thank the organizers for giving me the opportunity to present my work in this conference. I will present my recent work on effects of regularization and smooth transitions on the power spectrum of primary gravitational waves at high frequencies. This work has been done with Professor Jerome Martin, Arnab Pal, and Professor L. Siram Kumar. This is the brief outline of my today's talk. First, I will give the essentials of the primary gravitational waves, and then I will discuss about the behavior of the power spectrum in de Sitter inflation to radiation domination epoch, and subsequently in the matter domination epoch. Then I will give a motivation for regularizing the why we need to regularize the power spectrum, and specifically I will discuss a specific regularization method, adiabatic regularization method to regularize the power spectrum. Then I will discuss about the smooth transition from inflation to radiation domination and its effect on the power spectrum. I will conclude with a brief summary and the outlook. So inflation is an accelerated expansion of the early universe, which explains the isotropic nature of the cosmic microwave background or CMB. It is the quantum vacuum fluctuations which generate the perturbations during inflation, and it sets the inhomogeneities which we observe in the CMB. Largely, this is the scalar perturbations which is responsible for the such inhomogeneities present in the CMB. In addition with the scalar perturbations, there also exist the tensor perturbations which propagates through the universe as primary gravitational waves. The metric for such tensor perturbations can be expressed in terms of this. We can get the equation of motion for such metric in terms of as expressed as this, and as I said that it is the quantum vacuum fluctuations which generate the perturbations, so we need to quantize such tensor perturbations, and furthermore we can rewrite this equation of motion in terms of the new variable, that is Mukhanov-Sasaki variable, and so that our equation of motion turned into a time dependent harmonic oscillator equation. Now, from the observational perspective, it is the power spectrum, which is the power spectrum is a quantity which we observe. The tensor power spectrum is nothing but the two-point correlation function of the Fourier modes. The tensor power spectrum can be expressed in terms of tensor modes as this. During inflation, the behavior of the scale factor is given by this, where the L0 is the energy scale. L0 determines the energy scales of the inflation. And we assume the modes are well inside the Hubble radius at the very early universe, so that it never experienced the expansion of the universe and it behaves as a Minkowski mode. After implementing such initial condition, which is also known as a positive initial condition, we can solve the Mukhanov-Sasaki equation in terms of Hankel, exactly in terms of Hankel function, where the argument of the Hankel function mu equals to 3 by 2 and y equals to minus k eta. We assume the simplest scenario where the inflation, de Sitter inflation is followed by an instantaneous transition of the radiation domination epoch to the radiation domination epoch. The radiation and the scale factor expression during the radiation domination epoch is given by this, and for such epoch, we can get the general solution of the Mukhanov-Sasaki equation in terms of alpha kr and beta kr are the two Bogoliubov coefficient, and mk are nk are the modes. If we substitute the expression of the Mukhanov-Sasaki mode to the power spectrum expression, we can get the exact expression of the power spectrum. And furthermore, we can simplify this expression using the Wronskian condition of the Bogoliubov coefficients. We can see the expression like this during radiation domination. As I said, to get the to determine the eta r and ar of coefficients of the scale factor, we need to match the scale factor and its time derivative at the end of inflation to determine this ar and eta. By straightforward calculation, we can determine the ar and eta. Furthermore, to determine the modes, Bogoliubov coefficients, we can match the modes at the end of inflation, and to determine this alpha k and beta k, we can express like this, and by a straightforward calculation, we can show that the Bogoliubov coefficients behaves as this, where the y is k by ke. Ke is the mode which leaves the Hubble radius, and the last mode which leaves the Hubble radius during inflation. Now, substituting this alpha kr and beta kr in the power spectrum expression, we can get the exact expression during radiation domination of the power spectrum. We can easily show that the leading order contribution for the power spectrum for y much greater than 1, or the k greater than equivalent to k was greater than ke, is y squared. So the power spectrum behaves as k squared at the very small scales, at the very small scales. We have plotted the power spectrum at the time of equality for three different reheating temperatures. And we can see there are three different regions during this of the power spectrum. For this region, it corresponds to the modes which still outside the Hubble radius during the time of equality, and these are the modes which entered the Hubble radius during radiation domination, and it behaves as k to the power minus 2. And these are the modes which are never leave the Hubble radius, and they contribute to the k squared rise of the power spectrum. It is well known that the matter domination epoch is followed by the radiation domination epoch. So the scale factor for matter domination epoch is given by this, and the AM and eta m can be expressed in terms of AR and eta r, and we can express this. We can get these expressions by matching the scale factor and its time derivative at the time of equality. During the epoch of matter domination, the general solution is given by this for this matter domination epoch. The general solution is this, and alpha km and beta km are the two Bogoliubov coefficients during matter domination epoch. And qm, qk, and pk are the modes which can be expressed in terms of Hankel function. So if you just substitute the mode expression into the power spectrum expression, we can get this long expression. And to determine the alpha km and beta km in terms of the Bogoliubov coefficients during radiation domination, we can match the modes at the time of equality to get the expression. So we already determined what is the behavior of alpha kr and beta kr during radiation at the end of radiation domination epoch. So we can simply substitute this those expression into this, and if we substitute this alpha km and beta km into this expression, we will get the behavior of the power spectrum during matter domination epoch. If we substitute them, they are long and makes the exact expression. I don't want to show them in the slides, but to get the essence, we can see how the alpha km and beta km behaves at the y much greater than 1 limit. We can show that they behave similarly as alpha kr and beta kr in these limits. And also the power spectrum, we can expand the power spectrum, exact expression of the power spectrum in y much greater than 1 limit, and we can show that power spectrum again will behave as y square or the k square. Now again we have plotted the power spectrum for the three different reheating temperature, and you can see there are three distinct regions for the power spectrum. One is the scale invariant power spectrum, which still which corresponds to the modes which still outside the Hubble radius, and then the modes which enters the Hubble radius during matter domination epoch, and they behave for such those cases the power spectrum will behave as k to the power minus 4. And the modes which enters the Hubble radius during radiation domination, the power spectrum will behave as k to the power minus 2, and the power spectrum will behave in k square as expected for k greater than ke modes. So now we have plotted power spectrum for a specific reheating temperature, that is 10 to the power at the order of 10 to the power 16 GeV, so that it consistent with the tensor to scalar ratio. And we have also plotted the power spectrum, and now we want to see if this k squared rise can be detectable by the forthcoming or the ongoing GW observations. So we have evolved the power spectrum in terms of frequency. We have plotted in terms of frequency, and you can see that there are various GW observations present during this high frequency region. In this high frequency region, especially the CAST, which is Sun Axion Solar Telescope, it is actually ongoing observation, GW observation, ongoing indirect GW observations, and these observations still haven't detected any GW in this frequency. So, so it is indeed true that there is no such k square rise in the power spectrum, and we need to regularize the power spectrum. Furthermore, there is another aspect of why we need to regularize the power spectrum. That is, the signal which we observe by the GW detectors can be expressed in the x equals to 0 limit, that Dij into Hij where the Dij is a detected tensor and Hij is a mode at the coinciding limit. For the two-point correlation function of the such signals can be expressed as the integral of the tensor power spectrum. Now, if this tensor power spectrum has a k-square rise, then this integral will diverge and so that we actually need to regularize such power spectrum so that we get a physical observations. So we need to regularize the power spectrum. One of the simplest regularization technique is the adiabatic regularization technique. It is very effective in the time-dependent curved space-time. Curved space-time. Before going and implementing the adiabatic regularization, I will take a minute to explain the adiabatic regularization technique. This is a time-dependent harmonic oscillator equation, and to solve this harmonic oscillator equation, we can implement a WKB answers, and the answers is given by this. And if we substitute these answers into this equation, we can get this equation. And where we have added one adiabatic parameter as 1 over t, and whenever there is a time derivative, we add this time ordering parameter. This time ordering parameter helps us to get the different adiabatic orders. When we expand this adiabatic order, this wk, we will get a different time ordering parameter expression, and that will determine the different orders and different adiabatic orders. For such Mukhanov-Sasaki equation, we get the zeroth order. We can show that all the even adiabatic orders give a non-zero values, and all the odd adiabatic orders vanishes. So, and it is also well known that to regularize the power spectrum, we need till the second adiabatic order. So for our case, for the Mukhanov-Sasaki equation, the two zeroth order and the second order is given by this. Before going into the result, we can just simply discuss that what is the meaning of this adiabatic regularization in the real space. We know that the two-point correlation function in real space can be explained. The two different points can be expressed as an integral of the power spectrum in this manner. And if we put this adiabatic expression into this integral and perform the integral, we will get this expression. You can see for the a double prime by a is 0 for the radiation domination epoch. So for a coinciding limit, this actually diverges, and so actually when we are removing when we are subtracting this adiabatic term from the original power spectrum, we are actually removing the flat space-time correlation function. Now, in a generalized way, the adiabatic power spectrum expression can be given as this. And during the matter domination epoch, which is a mode of interest, which is a zone of interest for us, the expression of the adiabatic power spectrum is given by this. If we subtract it from the original expression which we derived earlier, we will get this regularized power spectrum expression as this. If you remember the power spectrum expression as this, there is 1 plus 2 beta and so on. So this is the leading order term which is responsible for this such k-square rise, and we have successfully removed this 1 plus term here after subtracting this adiabatic term. So we are able to truncate that 1 y square or k square behavior for the power spectrum. So we have now plotted the power spectrum for today, and we can see that the adiabatic regularization truncates this k squared rise, and it's able for k greater than k. Now it oscillates in a scale invariant manner. In the left side, we have plotted the power spectrum and performed the regularization just after the end of inflation to show how it oscillates. And you can see that that the early stage of radiation domination, if we perform the regulation at that time, it actually regularized, and it for the k greater than ke, the power spectrum behaves oscillates in a scale invariant manner. Now, if we smooth the transition, which is a realistic scenario that should be the case, in a smooth the transition from de Sitter inflation to radiation domination, we know the A double prime by A, which we'll call as effective potential, and during that inflation, the effective potential will behave as 2 by eta square, and radiation domination, it behaves as 0. If we introduce epoch as a linear function, so that it smooths the transition from inflation to radiation domination, and we have introduced such as a linear function. And now we can determine how the scale factor will behave during this smooth transition epoch, and we can solve this differential equation, and the general solution for such case as the Airy function. We can determine this a1 and a2 by matching the scale factor and its time derivative at the end of inflation, and you can get this a1 and a2 expression like this. And similarly, to get the AR and eta r for the radiation domination scale factor, we can match at eta e plus delta eta and get the exact expression. After having those two expressions, we can plot the scale factor analytically exactly, and this is the analytical behavior of the scale factor. This is the effective potential behavior. As I said, this is a 2 by eta square behavior at the inflation, during inflation, and 0 during radiation, and we have smoothed the transition by a simplest linear function. Now, what will be the behavior of the modes during this smooth transition? To get the analytical results, so what we can do, we can transform the Mukhanov-Sasaki equation into a new variable tau, and we can get the general solution for such equation as a Airy function, and determine this b1 and b2 coefficients by matching the mode function at the end of inflation. Similarly, to get the Bogoliubov coefficients of the radiation domination, we can match the modes at the end of transition, or eta e plus delta eta, to determine the alpha k r and beta k r. They are very messy and long expressions. They are in our paper. For the sake of simplicity and time, I have not expressed those equations in the slides, show that those in our slides, but they are in our paper. You can visit our paper. But to get the essence of the alpha k r and beta k r, and the behavior, we can expand the function Bogoliubov coefficient and see how it behaves in the y much greater than 1 limit, and you can see the beta kr it behaves as y cube instead of it behaves 1 over y square earlier. And also now we can get the exact expression of the power spectrum during matter domination epoch due to the smooth transition, and after the regularization we can get the power spectrum. Although this is not regularized yet, this is a term which will lead for y much greater than 1, but after regularizing we will remove this term, and the leading order term will be 1 over ye. That suggests that instead of scale invariant oscillation, we will now have a 1 over damping kind of 1 over y, 1 over k behavior oscillation. However, there is one term y square by x equals square that will be a scale invariant. For very ultra small scale, that is k greater than k cube by k cube square, the power spectrum will again start to behave the flat. So after k greater than ke, it will behave as k inverse, and very ultra small scale, it will again flat out. This suggests that we need to regularize, we need to smooth the transition between the radiation domination and the smooth matter domination. We have only smoothed the transition between inflation to radiation domination, but we have not smoothed the transition between radiation to matter domination. So we need to smooth the this transition. This is the plot of our power spectrum. You can see for k greater than ke, the power spectrum now behaves as k inverse, and this is again the regularized power spectrum at very early universe, early radiation domination epoch, and you can see for the instantaneous transition it behaves as scale invariant, but for the smooth transition it behaves as k inverse. So the power spectrum behaves as k square as we discussed, and we need to perform the adiabatic regularizations to truncate such k square rise. And furthermore, we have shown that for the smooth transition, after performing the smooth transition, now there is a suppression in power for the power spectrum for k greater than ke. In an ongoing work, we have furthermore showed that if we have a quadratic, cubic, and quintic higher order functions, smoothing functions, then we will get the higher suppressions. Actually, if we use a infinitely smooth transition, that is the effective potential is infinitely smooth at every higher order time derivative, and then you will get exponential suppression in the power spectrum. We have showed in our ongoing work, and we hope to publish it soon. Thank you.